Many industry LLM applications rely on a monolithic block of text, shaped by overlapping cursors, adding and deleting instructions in real time. This improvisation loop starts with one person writing instructions based on their initial assumptions of how the model should behave. When the results are inconsistent, others step in to edit the text, hoping to steer the output toward a better result. Contextual data is then bolted onto the prompt without defined boundaries, further increasing the complexity of the string. Eventually, the prompt might produce a usable output, but the team cannot identify which specific edit or data point was responsible for the success. This process is prompt improvisation. It relies on the intuition of the user rather than the logic of the system. Actual engineering requires structural standards. It requires repeatability, ensuring that instructions perform consistently across different runs and various users. And it requires measurable quality. Prompt engineering begins when teams move past these intuition-based edits and standardize their design, testing, and evaluation protocols. The goal is to construct an architectural framework that treats prompting as a rigorous operating discipline. Without this structure, a team has no way to debug a failure or confirm if a prompt edit will behave correctly in production at scale. To build a reliable pipeline, the chaotic text block must be dismantled and sorted into 3 distinct logical nodes: input structure, context boundaries, and instruction hierarchy. This architectural approach replaces the unpredictable nature of unstructured text with compartmentalized logic. The input structure defines the exact format for the data the model receives. This prevents the model from processing malformed variables that could lead to unexpected behavior. Context boundaries act as the second layer of the architecture. These boundaries define what information the model is permitted to use as a reference, creating a specific perimeter to mitigate hallucinations. The final layer is the instruction hierarchy. By establishing a hierarchy, developers can ensure that system-level constraints take priority over user inputs. These 3 components transform the prompt into a testable piece of software architecture. This modular structure aligns with how developers design API payloads in traditional software environments. This node-based organization is the prerequisite for building any reliable AI system. Even with a structured architecture, the system needs defined outcome parameters. The output path must flow through 2 logic gates: success criteria and failure conditions. Success criteria act as the primary filter for output validity. For a prompt to be deployable, the team must first quantify what a correct model response looks like. Failure conditions serve as the secondary gate. These gates screen for format breaks or unacceptable edge cases before the output ever reaches a production environment. These gates provide a binary evaluation for the model's probabilistic output. Every response is labeled as either a pass or a fail. This automated process removes the need for subjective, human-in-the-loop reviews for every individual run. Defining these gates is what allows for the implementation of automated unit testing. Without defined failure conditions, subtle regressions in the model's logic can bypass detection and reach the user. These gates translate the variability of AI generation into the predictable reliability required for software production. This telemetry dashboard processes the data coming from the logic gates, tracking performance across 7 distinct metrics. If an output clears the initial gates, these metrics provide the mathematical proof of its ongoing quality. This continuous telemetry replaces intermittent subjective evaluations with hard data. The first cluster of metrics monitors basic accuracy and the completeness of the output. A second cluster tracks reasoning quality and exact format compliance. The system also tracks the hallucination rate over time to manage long-term reliability. Finally, the dashboard monitors decision usefulness and tone consistency across thousands of automated runs. This visibility reveals subtle prompt decay that manual testing would likely miss. If these dimensions are not measured, any attempt to improve the system is based on guesswork. Telemetry allows developers to identify exactly which architectural component is responsible when performance drops. This level of precision is only possible when moving away from the trial and error approach. This telemetry layer provides the exact data necessary to refine the system based on evidence rather than intuition. This macroscopic view shows the complete pipeline. When a metric like format compliance fails on the dashboard, the system routes that data back to the instruction hierarchy node for recalibration. The architecture creates a closed, continuous feedback loop. If the telemetry dashboard detects a drop in compliance, the failure is immediately visible. Because the system is modular, developers can isolate the failure to the specific instruction hierarchy node. They can then make a targeted adjustment to that single node to address the failing metric. On the next run, the updated node restores the performance metric to acceptable levels. Introducing shared rubrics and evaluation metrics transforms prompting from an improvisational task into a controlled discipline. Prompt engineering is an organizational standard. It does not depend on an individual's clever writing. The discipline focuses on achieving standards, ensuring strict repeatability, and maintaining measurable quality. Implementing this telemetry-driven pipeline is the only way to transform large language models into predictable, reliable